I'm an independent data scientist in Paris, and today I will present you a project I've been working on. So it's an open source project in collaboration with the Information Retrieval Lab at Georgetown University, and it aims to offer a way of doing information retrieval for e-discovery applications. So let's start. So I'll start by introducing what is e-discovery used for and what it could be used for. Then review in detail the implementation of this library, and finally illustrate the information retrieval, say on an example of finding information in GitHub issues. So e-discovery is a procedure in the US and the UK. It doesn't exist in France, and it's a process in which electronic documents are retrieved for use in a legal investigation. So e-discovery represents approximately 35% of the total cost of litigation in the US, and as you know, probably there is a lot of litigation in the US. So it's a lengthy procedure in which you have to identify, collect, and find all the relevant documents for a given legal case. And and I will, in particular, be talking about the review process. So the review process is essentially a text classification task in which we iteratively search through the documents to find those that are relevant and remove those that are not relevant for a particular case. So traditionally, this was done with search engines, like 20 years ago. So essentially, you started by having an understanding what you were looking for in the case. You tried to express that in a few keywords. Then you looked at the results. You took the first few, and then you refined the search query to get better results, right? And this is specific to e-discovery, but this is also something we do every day, I guess, when we Google things and we don't find what we're looking for. We're going to refine the query. And this step of extracting features from our expressing what we're looking for in just a few keywords. This is not a very trivial task. So essentially, it requires to have some domain knowledge or some general understanding about what we're looking for. So sometimes we have a problem, and we just don't know what are the right keywords, right? And so, for instance, if we apply this to developers, I guess people who have more experience, they'll find things faster than those that are not. So there are several problems with this approach. Is that when applied to e-discovery, first is that it doesn't scale. So we cannot review that many documents. Nobody wants to look through a list of 100 pages of results of a search engine. Then we're not really designed to compose complex Boolean queries, right? Beyond a few words, we can't really do that. And a final way, which is particularly important in this case, is that it's really hard to assess, did we miss anything? So as we refine the query, we are getting more and more relevant results, but maybe there are some results which didn't contain those words, but were still relevant. So to address these limitations, in the last 15 years, there was a technology introduced which is called the technology-assisted review process, which essentially uses supervised machine learning and with a feedback loop where the user is going to submit some labels to the system. So he's going to label some documents. The system is going to predict the scores for all the documents in the data set. Then the legal, the lawyer is going to review some of the results, give new labels to the system until you converge, and this gives you better understanding how precise, what's the ratio of the total documents, total relevant documents that you found. It can give you more precision in terms of the full procedure. So this essentially, in terms of relevant topics, the e-discovery or the technology-assisted review is fairly close to personalized search engines or recommender systems. So in the first, we're looking for more relevant results. so in personalized search engines. For recommendation engines, you're typically content-based recommendation engines. We're going to try to discover content we didn't see before. And for e-discovery, the goal is to find both more relevant documents and to make sure we find as much as possible for a fixed review effort. So in the first two, typically, I mean, the systems we are used to every day, like Google or other recommendation engines online, we are not really in control of why the system gives us the results it's giving us. While e-discovery is more experiment in a very fixed environment, so we are explicitly controlling what we are training the system with. And of course, the personalization is going to be limited to a specific investigation. So let's talk about FreeDiscovery. So FreeDiscovery is an open source soft project built on top of scikit-learn and uses Python 3.5. So the API we're exposing is a REST API, because the people who are going to use it are typically in the Java world, so they can't use a Python API. And we also aim to eventually have some information retrieval methods that follow a scikit-learn compatible API. So the key features we have are document categorization and ranking, hierarchical clustering, near duplicate detection, and email threading. So let's walk through the text processing workflow, which is a fairly standard and conventional processing workflow for text. So we start by vectorizing text using bag-of-word model or n-grams, which gives us a sparse matrix for each text document. Then we do a dimensionality reduction using latent semantic analysis or LSA, which gives us a dense matrix for a dense vector for each document. And finally, we apply the processing algorithms to this. So for instance, for categorization and ranking, we could do like standard algorithms such as logistic regression, SVM, gradient boosting, etc. If we were looking for semantic search, we can do just nearest neighbors. We also do clustering where we have a hierarchy of clusters and we try to find the most relevant words for each subcluster. So like the most relevant keywords for each subcluster, and also duplicate detection. In addition, there is we had to implement an email threading algorithm. So I don't know if you know, the email protocol is it defines a few fields in the header which say which is the parent email to the email you're responding to. However, traditionally, those not all email clients respected that. So in the end, if you're building an email client, it has to try to do some heuristics and try to find the parent email, even if it doesn't have that information. So it's not a very deterministic process. Well, it's a deterministic process, but it's not very simple process. So all of these elements I just talked about are in this box, and then we need to talk with that through a REST API. So what we do, we add a persistence layer that's going to save the models and data on disk. Then we do a mapping layer. So when you work in this in discovery context, each document has a unique ID, and what you want to be able to do is to talk with the system using this unique ID, not, for instance, the row number in the NumPy array, right? Which is what, say, scikit-learn would be using as a reference for a given document. And finally, we build a REST API server on top of it that could be put behind the Nginx proxy optionally. So all of this is, except for the Nginx, is essentially a Python package which can be installed with Conda or pip and is cross-platform. So So let's talk about the REST API part. So we're just using a fairly standard components. We use Flask, Marshmallow, and WebArgs for serialization. We use the Flask built-in server for development and the Unicorn for production. And then we have this package which is called Flask API Spec, which essentially allows you to do a REST API, and at the same time it exposes an Open API specification which fully describes your REST API. So with this, we can then build documentation. Unfortunately, we couldn't like the documentation for the REST API. Sorry, unfortunately, we couldn't find a Python package that does that correctly. So we ended up using a package called Bootprint Open API, which is from Node.js that generates you HTML docs, but then they're not integrable with Sphinx, right? Because the main documentation is generated by Sphinx. So I'm not quite sure what's the consensus on how to do this correctly in the Python community. And finally, a challenge we experienced is that one of the constraints was we had to build this REST API because that's what people using it are going to be calling. But at the same time, we would like to talk with the system in Python. But developing both in a consistent way is not simple, and it takes a lot of resources. So in the end, we just ended up dropping the Python API because we couldn't just keep consistency all the way through. And so another solution is, say, to build a client library in Python for this REST API. For instance, you could use Swagger CodeGen, which is a library that can generate a client library in a number of languages based on the Open API specification. But that seems a bit complicated and not very robust. So let's walk through the text processing. So we use fairly standard vectorization approaches. We just extract document term frequency. Then we apply some feature weighting, such as inverse document frequency or sublinear term frequency. And then we also apply auto-normalization to account for variable document length. So in this case, it's fairly convenient because then we have a relationship between the Euclidean distance and the cosine similarity, and the later one is the one used to say how close are two documents. And this means that we can use a number of algorithms that are built just with the linear distance, and it's going to give an equivalent result as though we were using cosine similarity. So if you're interested in general text processing, there is 2 talks tomorrow. So 1 talk and 1 tutorial, and there's one talk earlier today. So once we have extracted our features from the documents, we apply dimensionality reduction, and then we, for instance, as a first step, we could apply clustering. So, for instance, here is a graph of hierarchical clustering of some documents. So we have a hierarchy of clusters, and for each subcluster, we have a few labels that describe it the best. So in terms of algorithm, we're using Birch currently, because that's the one which we find fairly scalable. So this approach is also used to create an efficient initial seed for categorization, because the initial seed should map as many should be mapped fairly consistently across the data set. So what we do is we essentially sample documents as a few documents per subcluster, and then this way we have a very uniform distribution across the data set that can be reviewed and used as initial training document set. So if you're interested generally in scalable clustering algorithms, there's a very good benchmark in HDBScan with linked here. So a second step is then to find near duplicates. So there are a number of ways that this could be done. So for instance, we could just say define a cosine similarity threshold, and use the GBScan algorithm, saying that documents which have a higher cosine similarity than this threshold are near duplicates. So the choice of the threshold is a bit arbitrary, and it depends really on the data, on what we're looking for, on our criteria. Another approach is for instance, the iMatch algorithm. In this one, we just work on the raw document term matrix. So we define a random lexicon, which maps a sum ratio of the vocabulary, and we say that two documents are near duplicates if this subset of the vocabulary is found in both documents, right? And then we do some iterations over a number of random lexicons. And finally, there's the local sensitivity hashing approach, which essentially allows for two documents that are similar to have a hash that differs only by a few bytes. So therefore, and we can query this fairly efficiently. So for this, we're using the simhashpy library. And like the difficulty in this is that we have different approaches, but then it's hard to tell how to find the equivalence between the parameters of different algorithms, or even what should be the threshold. So this is fairly subjective and depending on the field and on the data set. And so finally, we get to the categorization. So typically, what we're looking for is the recall curve. So what we here are plotted recall curves from the ERDM and run email dataset for different topics and for different feature weights. So this dataset was used to validate essentially FreeDiscovery and compare the results with the reference implementation in the field, which is the Turtle kit. So it's the technologist review toolkit developed. I can't remember where exactly in the US by a university. So by the way, it's, this one used Sophia ML library, which is a C++ library developed by Google, and had some bash processing scripts, right? So essentially, what we started when we started to work on FreeDiscovery, we implemented this in Python. So that was like the first step in this project. So what you see in these graphs is that is essentially you have the recall, which is the number of found documents as a ratio of total relevant documents in the data set, and in X you have the number of reviewed documents. So the review is expensive because you have to manually review documents. So what you want is to have a recall as high as possible with as little reviewed documents as possible, right? And so, for instance, on these graphs, we see that, for instance, the bag of words log TF-IDF is the one that gives the best recall curve. So more generally, we did quite a benchmark on like different parameters that could impact like recall. So, for instance, here's the recall at 20% of document reviewed and other standard metrics. And so what this table does is it compares the performance of these metrics with the baseline run that used logistic regression cross-validated using bag of words and log TF-IDF weights. And so what we see is that there isn't a single part of the pipeline which impacts performance, but essentially all parts do. So both you can choose, depending on the algorithm, on the parameters of the algorithm, you might get the different performance, but as well the feature engineering matters a lot in this case. So there are two difficult problems in e-discovery, or more generally in active learning, is when we have this active learning loop. So we have a reviewer which labels some documents, then takes some scores, reviews new documents, and then labels them. Essentially, the question is which documents should we take? So typically, what we do is what is often done, for instance, is to take those documents which has the lowest classification certainty. So, for instance, it could be a decision function which is close to 0, right? The high decision function would be like relevant documents and low being non-relevant. However, if we have a data set which is highly biased, so for instance, in the experiments we did, we had 1,000 relevant documents and almost 1 million non-relevant. So we cannot do that because otherwise we'll just end up with a training set which just contains documents from one class. So then we have to compensate for class imbalance, and essentially often it leads us to select just the the documents with the highest scores. And another point is the stopping rule. So we do these iterations, and the more we iterate, the more it's going to cost. But then we are going to find new documents. So the question is, what's the right stopping criteria? And there's different ways of doing this. So for instance, we can compute compute some metric for the newly reviewed documents and stop when this metric saturates, right? Or there's some statistical criteria to do that, but it's still a bit of a research problem. So another important point is that in the field of legal discovery, you need to be able to explain why a given document got included or excluded from the data set you're submitting to the court, right? So, for instance, let's take this. So this is a short email from the 20 news group data set, which is so the categorization was between two topics. Like there was two news groups, sorry. So one was comp graphics, the other one was SciSpace. So this one is from SciSpace. And here are the scores that are computed by, I think it was logistic regression. So the question is, can we explain those scores? And fundamentally, there are two ways we can do that. First is just with nearest neighbors. So we're going to compute the closest neighbor in both classes and say that, well, this document got categorized as SciSpace because it's closer to the similar document in SciSpace. And the second thing we can do is we can essentially try to visualize the importance of different features. So for instance, here we just implemented a way to visualize how much each of the words impacted, had an impact on the result, right? So what you see here is that, for instance, this document got categorized, like the words moon, planetary, and Mars are those that make it categorized as space. And documents like images, GIFs, and apparently thanks are those that getting it categorized as comp graphics, right? So apparently people thanks more in comp graphics. And so we did this for just in the case of linear case of logistic regression, but if you're interested in such things, you might, there is an interesting package called LE5 that I haven't tried yet, but that does essentially similar things in a more general framework and for not necessarily linear models. So also I would like to talk a bit about the specificity of this like the active learning system we have. So in a lot of predictive models, systems that have predictive models, what you have is essentially you have some fixed set of data that you train upon, and then the users are going to call the predict functions, right? So then this allows you to fine-tune the way you fit your model, choose the best model, and then even if the training takes a long time, such as in case of deep learning, it doesn't really matter because you can control that, you can run that in background, etc. In the case of active learning, that's not possible because essentially users are going to both run the fit, so they're going to train the model and predict it, and they expect the results which are below a few minutes. So, which means that essentially we have to, in this case, we are forced to use something which will give good accuracy or recall, no matter the training size, no matter the training data set, and which is typically means that we have to use simpler models, and as those are also rather fast than the more complex ones. Although we can pre-compute some pre-processing steps such as LSA or obviously feature extraction before like outside of this active learning loop. So let's look at the performance of different processing steps. So again, on this data set of 700,000 documents, which is the Enron data set. So the part that takes the longest are the two first steps. Those we can compute beforehand, so they're not really that problematic. What's a bit more problematic is that they scale with the number of documents. So typically it means that we need to well, we couldn't scale, say, to scale to 10 million documents. That would be already much more difficult. And also because we have the RAM requirements per million documents, which are approximately 15 gigabytes of RAM. So scaling would be much beyond that would be harder. And then if you run, for instance, semantic search, which is essentially just nearest neighbors calculations in the LSA space, we have a response time for like first page of results of around 2 seconds. And for to run supervised categorization and ranking, it's around 5 seconds. To compare that with, say, conventional search engines, they would give you a result in something around 50 milliseconds, right, for this data set. But they're also using like an inverted index, which is much more efficient for querying similar documents. But then you cannot do complicated things, like more complicated things with this that you can with machine learning. So just a few tips for optimizing some processing pipelines such as this one. So first thing, obviously, is that we need to benchmark and profile everything, because the intuition of what are the things that need to be optimized is not necessarily correct. For instance, we have the intuition that if we have an algorithm and then we run it in parallel, it's going always to be faster. Well, in a number of cases, that's not the case. For instance, if we do memory-bound computations, for instance, in Euclidean distances, and then we apply multiprocessing with jublib to it, it's actually going to decrease performance. Same thing with if we do nearest neighbor search using essentially optimized structures for that, such as KD tree or ball tree. In this particular case, where we have approximately 100 to 300 dimensions, it's actually slower than using just brute force nearest neighbors. So there's a lot of things we think might be better, but essentially until we benchmark them, we shouldn't be absolutely sure about it. Also, we were fairly reluctant to add other dependencies to the project originally, for instance, pandas. But in the end, this is really necessary if you want to do some data wrangling, something equivalent to like do joins with a reasonable performance. Doing that in just pure Python is extremely slow. And also, if you do serialization, so for instance, here we have essentially data which is stored in data frame, and you want to convert it to the dict that's going then to be converted to JSON. So if you just convert to the dict manually with a loop, it's like an order of magnitude slower than just using to dict pandas function. Also, there is some balance to be found between, like for instance, for the hashing vectorizer. If we want to scale the feature vectorization better, we can hash the vocabulary into predetermined hash table. This means that the transformer becomes stateless, and we can essentially parallelize it really well. The problem is that then we cannot we obfuscate the original vocabulary, and when we want, for instance, to compute the labels for the clusters, we can't do that anymore unless we try to invert the hashing, which is, well, I mean, it's another problem which I guess we can do approximately. So it's always a balance between whether we need really high performance or we need to keep access to the original document term frequency data. So I will just illustrate this quickly on an example of information retrieval on GitHub issues. So I'll take as example the scikit-learn project, which has currently 9,000 issues, and so approximately 90,000 comments, right? So if you want to find anything in there, well, there's the GitHub search, of course, but like the question was whether we can do something more efficiently. So let's take, for instance, this GitHub issue, which is about refitting the the time to refit the estimators in cross-validation. So like if we don't have a very good knowledge of the project, we're not really sure what are the right keywords. So to search for similar issues, right? So we could like, for instance, search for a time grid search, and we get almost 300 results. So then we might refine maybe the search query to find something more relevant. Again, so this really so the search query is going to be really dependent not so much on the text, but about our outside knowledge of what we know about the project, right? But at the same time, for instance, if we look at the results, even if we don't understand much about this issue, we can tell that some of the issues are probably not really relevant, right? So for instance, multiple metrics for grid search are probably not the thing we're looking for. So, so here's a quick example, like very simple example of analyzing like essentially all GitHub issues for this project. So we can essentially back up open source GitHub project on hard drive. There's tools to do that, and then you can just analyze the text as with any software you want. So here we have the feature extraction step. So we just essentially we just call some API endpoints. We tell them that there is some data here, and then the document ID. So essentially each document has an ID. So the document ID should be inferred from the file path, so from the file name essentially. And then we look at so these are the default parameters, which are essentially default parameters from scikit-learn. Then we will just apply semantic indexing. So we will say we want 150 components. So we will reduce our sparse document term matrix to just 150 components, and essentially this we will certainly lose some. Well, we will lose some information, but this way we can essentially use all the algorithms that depend on the distances. And then we can, for instance, run semantic search. So what we specify here, we specify the parent ID. So it's kind of a form of a pipelining result. So we specify the previous computational results, and then we say that we want to query document. So this is essentially the issue number, and then we get some documents, right, with a score. So those document IDs are again the issue number for the corresponding issue, and then we also, well, using pandas, we can just concatenate, you know, the actual name of the issue and the link to the issue, and then we can review whether this makes sense or not. Like with respect to the original query we had. So once we did just some simple search, the next step would be, for instance, to do categorization. So we will do very similar things, except that we will specify several documents, we'll give them a category, and then we'll sort the results based on the score for a given category, right? So, and iteratively, this way we can potentially, if we're looking for something, we can maybe find it with a higher certitude, even if we don't know the right keywords, or even if we're not sure what exactly we're looking for, but we can still, like looking at an issue, we can still say if it's relevant or not relevant, even if you don't know like much about the project. So essentially, this approach can help exploring connections between issues that are not explicitly linked. Well, for GitHub, it's probably not that like important because it has already this system of linking issues, and that work pretty well. And also, like our processing is probably not optimal because we just concatenate all comments. We don't handle them separately. We don't use any pre-processing for the code, etc. And like another possible project with similar goals could be like, for instance, to do bibliography review of archive articles. So there's like archive articles are in open access, so we can potentially just index them and then do something which is like review if we are looking for some topic, and we know which articles we're interested in and which we're not interested in. Even though we're not exactly sure what are the right keywords, we can converge towards something that might be of relevant. So I would like to just thank the contributors to FreeDiscovery, the people at Information Retrieval Lab at Georgetown University, and OneDiscovery for funding part of it. So to summarize, we presented an eDiscovery and information retrieval engine written in Python with a REST API. It was tested against published results with academic data sets. And while it is essentially designed for discovery use cases, it could be used for other information retrieval tasks, essentially being a content-based recommendation engine. So in future, what we would like to do is to improve scalability, possibly use a job queue or caching, although then it's not clear how to install still this as a single Python package, and possibly have some other related projects. So just the links to the documentation and the GitHub page. Thank you.